Again. 3, 2, 1. All right. Okay, let's continue talking about sets by talking about a specific type of set, the ordered set, which will form the backbone of pretty much a lot of what we're going to do. So it's good to isolate the notion of ordering and investigate it. So in your proofs class, maybe you got a little bit into this, but if not, let's go right in. So a set is said to be ordered if there is a subset of the Cartesian product of the set itself, where we rewrite an ordered pair being an element of the set as follows, because, right, this is just an absurd thing to write, although it is accurate, because again, remember, everything is a set, so even though, right, in ordering, we have, like, an intuitive idea of, oh, something is less than something else, everything needs to be a set, so, right, it exists as a subset of this thing, and we rewrite this in a more natural manner, similar to how we rewrite the output of a function as f of a, rather than, oh, you got these ordered pairs belonging to the set. And now, in order for a set A to be ordered, the ordering has to satisfy some things. Alright, so, everything is less than or equal to itself. That's hopefully not too offensive. If x is less than y, and y is less than x, then it's got to be that x and y are the same thing. Alright, and then some transitivity. If I know x is less than y, and y is less than z, then x is less than z. And then the final thing that we will include in our definition of ordered is that given any two elements, they are comparable, meaning that one is less than or equal to the other. Now, it's worth noting that this here technically gives us what's called a totally ordered or a linearly ordered set. We're just going to call this ordered, which is also what some people do. A partially ordered set has these three conditions. A pre-order, I think, is missing this part, which is called anti-symmetry. But anyway, for us, this would be the four principles of an ordered set. Our usual favorite sets of numbers are ordered, specifically the real numbers, which we are working our way towards currently. But before we get there, let's talk a little bit about ordering in a bit more detail. It's worth noting that there are other things that can be ordered besides the real numbers, so it's worthwhile to study this on its own. Alright, before we get deep into it, again, a lot of what we're doing here initially is setting up notations and also my general sort of approach to this stuff. I got, it's a typo there. Yeah, it's fine, you can just totally interchangeably use those. I want greater than or equal to. Alright. When it comes back, there it is. Hey, that fixes it. Yeah, so, we can use these two notations interchangeably, x less than or equal to y, or y greater than or equal to x. Preference doesn't really matter. Sometimes it makes a bit more sense to talk about something being greater than something else, rather than the less than. But, and like I said, I've already been saying it, when this holds, we say that x is less than or equal to y, or that y is greater than or equal to x, again, depending on how you want to look at it. And note something, the transitivity of ordering allows me to form expressions like this without having any issues. Right, this is a completely valid statement, and in fact, we write a lot of chains of equalities and inequalities like this. So where you'll have x is equal to y, which I know is less than z, which is less than w, which is equal to u. So from here, I'm able to conclude that x is indeed less than or equal to u. Alright, so something that we do a lot is strict inequality. In an ordered set, x is strictly less than y if x is less than or equal to y, and x and y are different from each other. Again, I have notes. And I did it again, where I have... Yeah, we can just interchangeably use those expressions. Let me fix that. Oh, man, I don't know what I was thinking with that. I know what I was thinking, I just put the wrong symbol. Alright, and so this is just the notion of strict less than. So it is worth noting that when you're studying things in general, you usually use less than or equal to, because you kind of don't know. But when you have specific numbers, right, you never use this, because you always know if they're equal or not equal, but one's less than or equal to the other. All right. Now that we've set it up, let's prove a couple of things about the strict ordering. That, first of all, it's not reflexive. It doesn't have the property that everything is less than itself, which, again, is sort of intuitively we know that, but, again, we're building everything from the beginning, so we gotta prove it. Right, and it's one of those things where it's like, well, this obviously isn't true, and you'll be shocked how often you actually use this fact in proofs, because a lot of proofs are basically going to be built off of, yeah, this can't hold, and I have this little thing called trichotomy here. All right. Okay. So first we'll verify that, then we'll verify that there is a transitiveness to strict inequality, and then we'll prove the big fact about strict inequality, which is the trichotomy property, meaning that if I take two elements, one of these three things needs to hold, and with that, that allows us to break down a lot of the theorems into basically just a couple of cases that you have to worry about. All right, well, so first things first, if this held, what does this mean? This means that x is less than or equal to x, and x is not equal to x, but x is itself, so that's contradictory. All right, now for the transitivity part, well, if this holds, then we have that, and if this holds, then we have this. So we know that the less than or equal to sign is transitive, so I can conclude that x is less than or equal to z. Now we just need to verify that x cannot actually equal z. So suppose that was true. All right, well, I have y is strictly less than z, and if x is equal to z, then I must have y is strictly less than x, and now what does that guarantee? Well, that guarantees y is less than or equal to x. But I have x is less than or equal to y, so that means I must have x is equal to y, but that contradicts that I have a strict inequality there. So it's got to be that x and z are different, so I've got the strict inequality. Nice. And point 3 is similar to point 2. Again, note point 3 is you've got less than or equal to here. You could also put less than or equal to here and have the same conclusion. It's essentially the same proof. Just, right, rather than using this to jump here, we just start with this. All right, so the big thing to prove, of course, was trichotomy, and there are, of course, 3 possibilities. Now, I do want to stress what trichotomy says again. It's not an or statement, it's an exactly one. So that means I need to prove that one of these holds, and then when one of them holds, the other ones don't. Right, it's an exclusive or, it's not an inclusive or. So when I'm verifying that one holds, I need to prove that the other 2 cannot possibly hold in that setting. So there are 3 cases that I have to do, and in each one I need to show one of them holds and the other 2's don't. Alright, so first of all, if x is equal to y, well then these can't hold, because these would imply x is not equal to y, so there we go. Alright, now suppose that x is not equal to y, and x is less than or equal to y. Now again, that would ensure that x is strictly less than y, so we have that this holds and that this doesn't. The only thing I need to do now is verify that y can't be strictly less than x, and like I said, hey, if that does hold, then 2, by transitivity, would give me x is strictly less than x, which contradicts point 1. So, like I said, you'll be shocked how often you actually use that very intuitive fact, but again, we're building from the beginning, it needs to be proven. Alright, so if x is equal to y, then these 2 can't hold. If this happens, then I have this strict, and I don't have equality, and I don't have the other strict inequality. So the last thing to consider now, by our assumptions on ordering, alright, well, if x is not equal to y, and x is not less than or equal to y, well, it's got to be that y is less than or equal to x. So I'm in one of these 3 possibilities. Either I have equality, or I don't have equality, and I have one of the inequalities. Alright, and now this goes basically exactly as the same proof goes, as the previous proof goes, because if I don't have equality and I've got this, well then I must have this strict inequality, but this strict inequality cannot hold, and equality cannot hold. So there are 3 possibilities, either exactly this is true, exactly this is true, or exactly this is true. Beautiful. Right, so again, note, this was an exclusive or, so I did need to run for all of the other possibilities not holding. It wasn't enough to just go, well, this holds in this case. Alright, cool. And trichotomy is going to be a property that we use quite a bit, so now we have it proven. Good times. Alright, let's continue talking about ordered sets, and So, like I said, you may have talked about ordered sets a little bit in your proof course, but something you may not have gotten super deep into was the notion of bounded above. So a subset in an ordered set is bounded above if there's an upper bound, meaning that there is some element in the set A, note, not necessarily in E, with the property that it's bigger than everything that lives in E. So E is bounded above. There is something that is always to the right of everything in E. And similarly, bounded below is defined in a similar manner with just everything's less than, everything's smaller. Okay, so it's going to turn out, especially for our purposes with real numbers and a lot of what we're going to actually do in this course, this turns out to be a very important concept. Right, and we saw this in calculus when we talked about finding minimums and maximums, right? You're finding, spots where I've got the biggest value possible of my function. And it's quite shocking that all of analysis can basically be built off of the back of these two ideas. So, quite interesting. Okay, so again, there's a lot of stuff you can now get into about what kind of sets are bounded above and which kind of sets are bounded below, and blah, blah, blah. But rather than, again, being completely exhaustive here, we can just prove some basic stuff to get a feel for how this stuff works. So what we'll prove is a characterization of when you're not an upper bound. So specifically, you're not an upper bound if I can find something in the set that is strictly bigger than you. Makes a bit of sense, right? But it's worth noting here in a moment with this proof that there's a very specific spot where we use one of our order properties that not every ordered set necessarily has. Alright, so suppose that B was not an upper bound. Okay. Then there has to be an x in E, so that x is not less than or equal to B. Right? Otherwise, B would be an upper bound by definition. Now, by trichotomy, that means that this has to hold. Because this can't hold, it's got to be that B is strictly less than x. Now, note, trichotomy we got from the fact that any two elements are comparable. And like I said, technically a partially ordered set doesn't have that property, but for our purposes, we don't care. We want that property as we're focusing on the real numbers. So it's worth noting this proof does not extend to more generally ordered sets, but the things that we're calling ordered will have this property. All right, now similarly, suppose that there was an x that was strictly bigger than b. If b was an upper bound, then this would hold, but then by transitivity, we would have b is strictly less than b, which is contradictory. So b can't be an upper bound. And the analogous things for lower bound are similarly proven. We don't need to get too sweaty about the details there. All right, cool. Well, there we go. And that's... there we go, a little experience of proving things with upper bounds. All right, so amongst upper bounds, the ones that are the most important are the least ones. Okay, so for an ordered set and a subset, a upper bound is called a least upper bound if it itself is an upper bound, and it's smaller than all other possible upper bounds. Okay, so note that there's kind of a flip here, right? We're talking about things that are bigger than every element in E, and then we're talking about the smallest possible one you can find. Right, and note that you would want least upper bound. There's no such thing as greatest upper bound, because if you have an upper bound, anything bigger than it is still going to be an upper bound. So, right, and if we're thinking about the real numbers, right, if you've got, like, oh, my set's bounded above by 7, well, then it's bounded above by 8, 9, 10, 11, so on and so forth. Right, greatest upper bound is not interesting. Least upper bound, on the other hand, though, turns out to be the key ingredient of the real numbers. All right, cool. So that's what a least upper bound. It's also known as a supremum. So I'll use those two phrases interchangeably. But basically, right, the smallest possible upper bound. Now, note, this may or may not exist. Right? There's nothing saying it has to. But if you have one existing, it's got to be unique. Because if you have two least upper bounds, they have to actually equal each other. So let's see a proof of that. All right, well, since alpha is an upper bound, and we've assumed beta is a least upper bound, well, it needs to be smaller than every possible upper bound, so it's less than alpha. And a similar argument applies since beta is an upper bound and alpha is assumed a least upper bound, it must be less than beta, so they have to equal each other. And similarly for greatest lower bound. Alright, so if we've got an ordered set and it has a least upper bound, it's got to be unique, and we give it the following proprietary notation, soup of E. Sup E. Yeah, there we go. And similarly for greatest lower bound, we'll use inf for infimum. So it's worth noting that soup and imp is kind of a newer naming for this stuff. If you go to an older book, you'll actually see lub instead of soup. So least upper bound, and for greatest lower bound, you'll see glub. I don't know exactly when supremum and infimum became the names that took over. Soup and inf look a little bit, I don't know, cooler, maybe? I don't know. Somebody just wanted to just say sup all the time, I guess. Yeah. But, yeah, so least upper bound. So these used to be lub and glub. Now they're soup and inf. Alright, so let's, prove something that we'll use quite frequently, and specifically what we'll use is actually the negation of the statement, but it's worth proving. So, if you have a supremum, then you can determine if something is an upper bound, because in order for it to actually be an upper bound, it must be greater than the supremum, right? The supremum is the smallest possible upper bound. So the only way you've got something that's an upper bound is if it's actually less than or equal to your supremum. So, what we'll actually use here is this is one of these statements that you prove in mathematics, and you don't actually use the statement itself, you rather use its negation. It's just easier to prove the statement, and then its negation is the useful one, because it turns out that we are going to have things less than a soup, and that means it can't be an upper bound, and we just proved a characterization of things that are not upper bounds, that are pretty useful. Alright. Okay, so, again, this is a nice, straightforward, and simple proof, so let's go through it. Suppose that B was an upper bound for E. Alright, well then, soup E is the smallest one, so that's got to hold. Alright, likewise, suppose you had something bigger than the soup. Alright, well everything that lives in E has to be less than or equal to the soup, because it's an upper bound, and then by transitivity it must be less than B. So B's got to be an upper bound. That's it. Right, no, this was not a tricky proof. Like I said, a lot of these proofs here initially, right, there's no, creative part to it. These are mostly just unraveling definitions and setting up tools we're going to use later. But yeah, so, not a bad proof. Nice and straightforward, and it's going to be very useful, as you'll see. Alright. Now, let's actually do something that is a bit tricky of a proof. Okay. So an ordered set has what we call the least upper bound property if every non-empty bounded above subset has a supremum. Right, so like I said, there's nothing immediately saying that a bounded set has to have a supremum. And in fact, it's possible that you don't. And we'll talk about that a little bit later. But a set with that property, we say it's got the least upper bound property. You'll also see some people call this Dedekind completeness, and that's because a mathematician named Dedekind is the one who figured out that, this is very important, because as we'll see, this ends up being the key property of the real numbers. Alright, so, I don't have a pause. Excuse me. Oh my god. It's every time. I think I got the slides, and then there's just something that I miss. Yeah. Alright, anyway. Okay, so what we're going to prove now is that if you do have the least upper bound property, you also have the greatest lower bound property. Meaning that if you have a non-empty and bounded below set, it has an infimum. So actually, it didn't matter that you started with, every non-empty bounded above set is a supremum. We could have done every non-empty bounded below as an infimum. It doesn't matter. Alright, And something you might be asking, of course, is the non-empty. Why is that thrown into the definition? And you'll see where it shows up in this proof here, and why you need it, otherwise you can't really do anything. Alright, so let's go ahead and do this proof. So what do we need to prove here? So we're being asked to prove that if you've got a non-empty set that's bounded below, it's got an infimum, under the auspice of a set with the least upper bound property. Alright, so how would you approach this? Well, think about what the least upper bound property says. If I've got a non-empty bounded above subset, I can find a supremum. So I need a non-empty set, I need to be bounded above, then I can invoke a supremum. Right, so think about the hypotheses that we have. I have to somehow invoke this to demonstrate the existence of an infimum. Well, I can create the existence of a supremum, so I need a non-empty set that's bounded above. So how about we look at the collection of lower bounds for E? Note, our hypothesis guarantees that the set is non-empty, because, our set's bounded below, so it has lower bounds, so this set is non-empty. And now, since E itself is non-empty, we can fix an element. Note that anything that lives in B, since B is the set of lower bounds, has to be less than or equal to A, so that means A is actually an upper bound for B. So B is a non-empty, bounded above set, so it must have a supremum. So I've now actually invoked my hypothesis. So again, that's a good check but a proof to make sure that nothing screwy is going on. If I never actually used my hypothesis, that would be a problem. Right. But indeed, we are actually using it. Okay, so the claim now obviously is that the infimum of this set is in fact the supremum of E. And that makes sense, because if you think about all of the upper bound, if you think about all of the lower bounds for E, those are all to the left, and the infimum has to be the biggest thing right. Well, everything in the set of lower bounds that are to the left of E, everything on the right, everything that's in E, those are upper bounds for the set B. So you just need to push yourself all the way as far as you can go, the maximum there, right? And that would, of course, be the supremum, the biggest thing, the smallest, biggest thing that you could find. All right. Okay, so we just need to verify that the supremum of B is the infimum of E. Alright, well, let's let alpha be the sup of B. So I have two things to show. I gotta show that it is a lower bound of the set E, and that any other lower bound of E is less than it. Right, because I want to show it's the greatest lower bound. Alright, so fact number one, we need to show it's a lower bound, so pick an element that lives in E. For any B that lives in capital B, that's a lower bound for the set, so that means B needs to be less than or equal to X. So that means any element of E is in fact an upper bound of B. Alpha is the sup of that set, so it needs to be less than or equal to it, so that means alpha must be a lower bound for E. Alright, okay, so note that this was kind of just a reformatting of a proof we already did. Right, where we noted that the set B is bounded above by anything that lives in E. So pick anything in E, it's an upper bound. Well, the least upper bound must be less than or equal to it, so we get that. And that gives us that alpha is a lower bound. Beautiful. Alright, now we just need to verify that it is in fact the greatest lower bound, so take a lower bound for E. Alright, well, that means that it has to live in the set B. But B is bounded above by alpha. Right, that's what this means. It's an upper bound for the set B, so B is in the set B, which means it's less than or equal to alpha. So alpha is a lower bound for E, and it's bigger than any other lower bound you can think of. Thus, it's the greatest lower bound. And the proof's over. There we go. So, that was kind of our first proof that had a bit more going on to it, a little bit more than just sort of unraveling definitions and just following the thread. This actually had like a mild, clever part, but if you really look at all the components, all of the ingredients of the proof, and this is a proof that I love because of this, all of the assumptions, non-empty, bounded above, non-empty, bounded below, least upper bound property, all of them are being used and they're kind of being used precisely once, right? Right, I want to show that the set E has an infimum. Well, let me look at its collection of lower bounds. I need to find the biggest, I need to show the set has a biggest element. Well, by its hypotheses here, we know that it's non-empty. And since E is non-empty, we know that this set has to be bounded above. And now by the least bound property, we get our supremum, which gives us our biggest element, which must be the infimum that we're looking for. Because I'm looking, again, for the greatest lower bound. Beautiful. All right. Good stuff. All right. Yep. And then, as the actual proof goes, right, the key maneuvering here was the noting that everything that lives in E is, in fact, an upper bound for all the elements of B. So the soup showing up is a... right, that allows us to sort of sneak in this maneuvering right here, that it's the least upper bound. So, yeah. All right. Cool. Good stuff. All right. Okay, one final bit of bookkeeping is the idea of a maximum and the idea of a minimum. And these are just precisely soups and imps that actually live in the set. So, as we will see, it's very possible that you do have a supremum, but your supremum actually isn't in your set. But when it is, then we call that a maximum. And it's actually pretty easy to detect maximum because if you have an upper bound and it lives in your set, then it has to be the max. Okay. So, and similarly for mins, and if you're a lower bound, you live in the set, you're the minimum. All right, well, let's finish this up. So, we say that E has a maximum, if E has a supremum, and sup E lives in E. All right. Well, I have an upper bound that lives in E. I want to show that it's the supremum, because then it's the supremum in the set, thus it's a maximum. Okay, well, if I take an upper bound, well, M lives in E, so it's got to be less than or equal to B. But that means M is a lower bound that's less than every other lower bound, so it's got to be the soup. And since it belongs to the set, it's the maximum. And the proof's over. That simple. You're right. I'm not jerking your chain. That's straightforward. All right, cool. So there we go. That covers all. All right, so let's landing with a nice, very simple, straightforward, clarifying proof. All right, and so it's that simple. All right, so we have established what ordered sets are. We have got upper bounds. We've got soups. We've got mins and maxes. All right, and that's all we need from ordered sets. All right, so we're almost there to getting to the real numbers. We just got one more pit stop to make, and that's the idea of a ordered field. Ooh, so that's what we'll talk about next time.